In this video, we're going to introduce the last major topic for the course, looking at functions of two variables, and as we'll see going forward, possibly three or more variables. To motivate this, we consider a nice concrete example, looking at temperature distributions on Ontario on a particular summer day. What we can see, if we look at the map on the next page, is that the landmass of Ontario here has a fairly complicated shoreline, but we can see up here, if we imagine the lakes in the corner here, that we can capture the temperature at different towns or simply different locations in Ontario on a given day. Looking at the scale of the map and the layout here, what we see is that we're probably up around Kingston here, down near Windsor here, Toronto in the middle, and we've got the northern ends of southern Ontario on the map up here. We can see there's a variation in the temperatures, colder up here, 21 degrees, down to about 27.5, down towards the Windsor end of things. Now, what is new about this kind of relationship is that if we wanted to find the temperature at a point, and that is something we might call T, what information do we need to specify? Well, if we take a look at the map here and say we want to specify the temperature here, we need to specify two inputs. We need to specify the latitude, and we also need to specify the longitude that matches that point. And so we have two inputs that we need to specify. Longitude and latitude. Until we specify both of those, we don't have a single temperature point. For example, if we just said, oh, I'm at latitude 43.5 north, then that could correspond to any temperature along this range. There's no single output until we also commit to a longitude value. With that in mind, this is how we can translate our earlier functions into a new syntax or a new set of symbols. We would say the temperature depends on x and y, or in brackets x, y are the inputs to that function, versus earlier, where we had a function of x, that had a single input, and it was a one variable function. When we talk about variables, we're talking about the inputs for the function. Whereas what we've just created is now a two variable function. And what we're going to see is how calculus has to get extended or modified from what we've seen earlier to apply to this new kind of function. If we want to get a little more formal, we would say that a function of two variables is a rule, just like any calculation rule we've seen before. The difference is now that we're going to take pairs of numbers as the inputs. When we get values back, we're going to get a definite output number, and an important ingredient here is that it's going to be a single number. So we would have x and y, those would be the inputs. They will lead to a single value back, which would be your temperature value. The set of all input pairs is going to be called the domain, and the resulting output numbers is the range. That's the same terminology that was used when we were looking at single variable functions as well. That changes a little bit in interpretation though, because the inputs are pairs of real numbers, and so those are points that we could represent in the xy plane. And if that's the case, then the set of values that work for a function would be some region in the xy plane, not an interval like it used to be, but some set of xy pairs that work with the function. The output is a single real number though, so that doesn't change. That's going to be an interval of the real line. If we return to our temperature in Ontario example, and we note that there are regions where the function is not defined because there's a lake there, it's not on land, then what we have is a region that would be the domain of our temperature function. All the longitudes and latitude pairs that work are in this region here, and that's a region in a two-dimensional space, or the xy plane. If we next want to look at the range, remember the range is about the output values, There we can see that the temperatures are single numbers, and depending on where we are, they range from 21 degrees down to, it looks like 27.5 is the highest here. And so we would say that the range of T of xy is the set of all values between 21 and 27.5. And we would interpret that in this scenario as, on this particular day in July, the maximum temperatures in the region shown vary between 21 and 27.5 degrees Celsius. Now, just with that simple example, we see that there's more complexity here than there would have been if we were looking at single variable functions. Fortunately, we are still building off all of the work that we've done before when we look at a graph like this, or a table of values, or imagine this as a function, because what we can do is take this two-input function and bring it back to what we know, a single variable function. And one way to do that is imagine if we're traveling from Toronto at approximate latitude 43, so up here, longitude 79.5, so that's Toronto. And if we go to North Bay, which is a different latitude, but actually the same longitude, so we're going up to 46.5 up here, then we can imagine traveling on the map. I'm just going to go back a moment here. If we look at the map and imagine traveling from Toronto up to North Bay, then what we see as we drive along that road is a single set of temperatures as we traverse the road. What do we mean by that? Well, if we measure the distance from Toronto along this axis here, so this is TO down here with 0 kilometers, and we have, say, North Bay out here, what we would see is temperatures along that path. And notice it doesn't matter that there's another direction we could go in, because all we're doing for this particular experiment is driving along this single straight line. And what that gives us is a function that starts at 25.5, then goes to 25, then goes down to 23, then 22 and 23 and 24, and 23 and 21. So we can sketch out a graph of, if I move a point here for North Bay, the temperatures along that road. What would we experience? What would you see in your dashboard as you did the trip on that day? And this is a regular single variable function like we know and love. We could talk about maxima, we could talk about slopes, we could talk about tangent lines. All of the technology we've built for functions of single variables would apply to this particular subset of this big temperature map. We're going to take advantage of this idea of following a single path through a two-dimensional space many, many times over the next several weeks, because what it gives us is a return to what we know already about calculus of single variables that we can then leverage back into the more complicated two-variable problems. It's worth noting that there are multiple ways to do this, of course. We had a relatively obvious construction in that Toronto to North Bay, we simply went north. Obviously, we could go east to west as well. We could go west of Toronto and travel along roads that way. Perhaps a more interesting way would be to imagine, going back to the map for a second here, there's actually a road that would come from this end of Ontario through Toronto and up to about Kingston and onwards, and that would be the 401 highway. We could do the same thing we talked about in terms of our transit from Toronto to North Bay, but we could do the tracking of our temperature as we travel along the 401 corridor. And so if we talk about the distance from Windsor along the 401, then we would see the same kind of pattern. We'd start up that high temperature, 27.5, then it would come down, and by the time we're done, we'd end up at 24. So we would see 27.5, and as we go along the corridor, we would see 27s, 26s, 25s, 24s. So we would see some kind of gradual decline in the temperatures, where we have Toronto in the middle here and Kingston at this end. In other words, the path that we take does not need to be strictly along the axes of our normal xy directions. They can be along some other path as well. If we did that, but also opens the door for any other pathway, we can imagine following other highways in through the backcountry of Ontario and generating temperature graphs that way. The idea is, if we have a two-variable function, we can always talk about a path through that domain of that function. And if we look at the value of the function, here temperature, along that path, we get a nice single variable relationship like we've seen before.